Okay, so before we get into feature, good morning, everyone. How are you doing? So mostly what we're going to do today is do some ideas about kind of feature extraction and actually converting our nice masks into data. But before that, I felt like yesterday the very end of the class was a bit rushed, and so we kind of skimmed through things in a way that wasn't very useful for anyone, I think. And so we're going to kind of redo just the last bit of yesterday. And also I misspoke on one of the points here on exactly how to pick these markers. And so we're going to kind of correct the record. Okay. So yesterday we kind of skimmed through this, and so let's kind of go line by line and see that we understand what's exactly going on here. Specifically, the function that we kind of really breezed through without explaining was this peak local max function, which is actually a very powerful and important function, and it does most of the heavy lifting in this specific cell. So all of this, okay, you understand, all of getting everything in. We make our mask by doing this kind of smoothing to get rid of salt and pepper noise, and then just take everything that's bigger than this triangle threshold that we calculated before. Is this clear to everyone? Yeah, the idea of like how triangle threshold works is kind of something we talked about yesterday. Then we take our data, we mask it, okay? We do a Gaussian smoothing on this data. So we use a sigma of whatever, 3, 4, you can pick a number, and then we invert this, right? And this presumably gives us an image with kind of dips wherever we have cells, right? And relatively smooth dips. And now this function peak local max, okay? So so peak local max finds as it you can probably guess local maxima, right? So first of all, this image to watershed that we made has local minima where we want to find cells. So we first need to invert it again. So this is we can probably just put kind of switch the lines, and then we don't have to invert twice. But the idea is just to make sure that our peaks are at a peak. Now, peak local max has this argument called footprint, and it basically says it says local max, right? So it asks what is the local when local max. And so when I say that the footprint is, let's say here, 1s 30 by 30. So this is just kind of like a structuring element. So a square, 30 by 30. And I'm saying in every square that's 30 by 30, find the local like maxima there, right? So if I have multiple little maxima there, it's going to find the highest one of them all. So let's say this is my, okay, if my footprint is 30, so it's going to look at all of these 30 pixels, let's say, and it's going to return only this one, right? And so this also does a lot to remove kind of noise. Now I can play around with it, and we're going to do that for a few minutes just to see how changing this window affects our segmentation. So you can imagine that if the window was smaller, for instance, like this, I would find both this peak and, let's say, this peak. And so the size of the window needs to depend kind of on the features that we're looking for.
What's at the next window? Does it just shift by one?
So it does, it kind of, go through everything. But it makes sure that there are no two maxima that are closer than 30 pixels. So close, that can sit in the same footprint. So this input can be in a 2D array, probably also a 3D array, honestly, depending on if the image is 3-dimensional. And it needs to be like binary, right? So it needs to be. So this is basically a structuring element, and you can make it a disk, you can make it a diamond, you can make it whatever you want. This probably we don't need because I'm not giving anything. But this, there is this. Do I want to include or exclude maxima that are on the border? So if you look at our original image, you see that like this cell would have a maxima that's right on the border, or this cell and stuff like that. Sometimes you want to exclude these just because they're not whole cells, they're kind of weird. It would be hard to like get statistics from them, because how am I supposed to compare this to this, right? And so you can choose whether you want to include or exclude these. And this is just a parameter called exclude border true or false. And indices, so this peak local max can either return an image with just points where, with positive points wherever you have peaks, or the indices of these peaks, right? So this is an image, so it can just give you, like, instead of a whole, and this returning indices is good for memory, because instead of giving you 1,000 by 1,000 numbers, it gives you, I don't know, the 50 by 2 numbers, right? So it can save some memory, but it's a bit more annoying to work with, because instead of working with an image that we now know and love, we're working with just the list. And working with the list, we will need to do some other processing. So for now, we'll set this to false. And this is just changing it to an integer, so we can work more easily with it. Okay, so because these I know are going to be integers because they're pixel positions. Or sorry, like zeros and ones. So I don't want them to be like true or false. I want them to be 0 and 1. Okay, now this is actually a different technique that we can use. In this case, all this does is make it easier for us to see where the peaks are, right? So if we expand the peaks, the 1 point peaks into kind of a region, it would be easier for us to see them like here, right? So if this was just 1 pixel, we wouldn't be able to see anything. But practically, it doesn't make any difference if it's one point or a circle. We can, instead of doing this, find all local maxima, and then by expanding, we can combine them. And this does work. It's just kind of a different technique. So in this case, this only serves kind of for presentation purposes, right? It's for us to be able to see, but we can, if we give this or this as the markers, it should be equivalent, right? So we'll check to see if that's true. I hope that's true. So and then we just run watershed. We have this image to watershed, which is what we started with. We have the markers. We want to have a watershed line, and we have the mask. This is like not new, right? So this is what we get. You see that when I say, I don't ask it to exclude the border, so I include the border. Now I get all these cells that are kind of on the edge, for better or for worse. Let's see what happens if I exclude the border. You see that suddenly these cells aren't retained, right? And again, sometimes this is a good thing, sometimes this is a bad thing, depending on what we need to do. And the other thing, and I'm going to let you play around with like changing these numbers and seeing how this affects stuff. If we use for markers, so markers have to be labeled, right? This is a binary image, so we need to do measure.label of this binary image. This should presumably give us the exact same type of segmentation, right? So the markers don't have to be a region, they can be a single point. They just have to be an area with some value, some like minimum value. Okay, so let's take the few minutes that we didn't have yesterday and just play around with these numbers, see how changing these structural elements, you can make them into a disk, you can make them into whatever, you can change the size and see how that affects your segmentation, okay? So let's do that for like 5 minutes, okay? All right. So I hope you got to kind of experiment a little bit with what these different inputs do. Of course.
Is there a way to find out, what is the way to find out how many it's labeled?
How many it's labeled?
Yeah.
Aha. So that's a good question, and this is kind of what we're going to do. I'm going to say ahead of time that today is going to be slightly less interactive, just because we've already done the hard bit, right? So we found individual objects. Now, for the most part, Python is going to do the work for us. So it's kind of one function that does all or much of the feature extraction. And on top of that, we can, of course, do more. But the heavy lifting is again going to be done by this one function. Now, what is exactly feature extraction? On the first day, we talked about this idea that we want to take an image, something we took of the world, and convert it to kind of a list of objects with different attributes, right? And this is something we can go and analyze and learn something from. And so now we're at the stage where we recognize that this is one object, and this is another object, and this is another object, and we just need to extract that information out of it, right? So the relevant function is called region props. So region props accepts a labeled mask. So in our case, label local max markers, whatever is the labeled max. And it can also accept an image. So an image is not necessary, but it can return more features if you also give it the raw image that you started with. And it returns a long list of features. Okay, so, sorry. it returns a long list of objects, and every object has a bunch of features. Okay, so let's go to this list over here. So you see there is like, see the full list here. And kind of scroll down and see exactly what we can get out of this function. And then we're going to see how we get it out. Cool. So we can get the area of the whole region. Right, so this is not just the, so the area of all the pixels that are within our mask. Right? So this does not depend on the intensity. A bounding box, so just kind of a region where the cell is. Sometimes we want to like mark around the cell and say this is where it is. We can get the area of that bounding box. We can get where that object is, so the centroid. So it's just an X and Y position. It can be convex area. So if our object looks like something like this, convex area is, think about it like a rubber. If you took a rubber band and you just put it around, so the rubber band would not go into all the crevices. It would just go and do something like this. So this would be the convex area, right? So it will not bend into places. Convex image, so this would be the actual image. So the area would just give you how many pixels are in there, and the image would give you, let's see, the return kind of a mask that is the convex mask of this bit. Coordinate list, so just all the pixels, not just the center, all the pixels that we found, where are they? And it would be kind of 2, so xy by the number of pixels we found. Eccentricity, so eccentricity is the ratio of how long the major axis to how long the minor axis is. So you can say if this is stretched out or more round. Equivalent diameter, if instead of whatever shape it is, it was a circle, what would be the circle's diameter? So this is kind of a measure of size. Euler number, whether it has holes in it. So some shapes have holes in them, and this is topologically an interesting number, so it returns that. I'm going to go over all of them. There are a lot. Extent, so something area over rows times columns. Let's go to some more interesting bits. So image is just the ratio, the mask of that area. Intensity image, this is an important one. So this would give you, if you also provide the image itself, so the raw image, and we're going to see this in a minute, it's going to give you in that bounding box an image of your single cell, so or single object, right? So we're going to look at that. Label, just the number that this was assigned to when you put it in. Local centroid, so sometimes it's a centroid compared to the bounding box, okay? Because the global centroid is compared to the whole image, and the local centroid is compared to the bounding box. So sometimes you'd want to analyze each bounding box individually. Maximum intensity, mean intensity, and minimum intensity, these are important, right? Sometimes you really want to analyze how intensity of some cell changes, let's say over time, or whether some cells are brighter than other cells, and this is how you get that. Orientation, perimeter is also kind of, size. Weighted centroid. So if you have an object that is not uniformly, like the intensity is not uniform, right? So for instance, an object that it looks like this, but this size is very, very, very bright, and this size is very, very dark. So weighted centroid would weight the position. A normal centroid would just give you this. A weighted centroid would weight the position of the centroid by the intensity. So it could give you something more like here. And so, for instance, if you're tracking, this is, it's good to kind of get around if you have some slight segmentation problems. So if you capture bigger regions than you should, then this would kind of fix it. So you don't have like a centroid in the middle of the ocean. Weighted local centroid, so compared to the bounding box, and more or less that. You can go over specific things, and depending on your application, you might want to use something I didn't mention, but this is kind of the major ones. Okay, so how do we actually get these things? So from SK image, we get measure, and just measure dot region props is what we care about. We feed it the mask that we just calculated and the image of the nuclei. Cool. Now you ask, how do I know how many cells I have? So there are a few options. One option is to extract the region props. So do this, and then just the length of this list is going to be the number of features I found. Another option is to just say, what is the maximum number that this one has, right? So they're labeled from 1 to the number of cells, and you can just say, what is the maximum number that I got? So this should give you the same number. So let's see what happens. So maybe so I just split the cells so we can kind of run them separately. So this is just extracting these props. I have 229 cells, right? And let's kind of see what this guy is. So you see each one of these things, it's a list, and each one of each object in this list is an instance of region properties, right? So it's an object. So this is important. And then how do we extract anything from this object? So let's say I want to look at the first one of them. Props 0. So it would again tell me that it is an object, but it's an object with different properties. So what are these properties? We said that areas is one of them. Bounding box. See, so I can for each one of them I can extract whatever I want. So let's say the maximum intensity of the first region is 0.012 something. Okay. And so you can do this for each one and see different things. Now, of course, we don't want to go one by one over all of our just change 1, 2, whatever, and just one by one look and make a list with Excel. We want to have kind of a better way of extracting a lot of them together, right? So the way we do this is, so this is one simple way of doing it. So we're just going to run a loop over all of these properties, so all of this list. And for every object in this list, we're going to extract areas and intensities. Cool. And then let's just do just a histogram of both, just to show what we have. So you see that the areas are pretty uniform, which is actually usually what you'd expect if you have uniform objects. Intensities are kind of more widely distributed, and if you look at your original image, this is something somewhere. This is something that you should expect, right? So this is our somewhere. That's far away. Yeah, so you see there is some distribution of intensities, and you'd expect to get kind of a wider distribution of intensities versus areas. This is also a good place to verify that you didn't mess up your segmentation. So if you get something that looks really off, like many of the objects are really, really tiny or really, really large, then you have some issues. Or if you have kind of very different objects when you expect similar objects. So this is something to keep in mind back here. Okay, now this is something that I noticed yesterday that was kind of lacking in the notebooks that you have. This will be updated on the repository and you can download it. There was kind of a lack of presentation. So how do we actually present this data and kind of look at it in a more visual way? And so we can look at an individual object that we find and see whether this is a good let's say, good cell. We can kind of do some quality control. So the way we do this is by just showing the intensity image of a single cell, right? So of a single object. So we said that this list contains all of these properties for every object, and we can just plot plot as an image this one property, which is the intensity image. So let's say I can change this number, and this would give me different cells. So you see this looks like a really nice cell, right? Nice and uniform. If I try hard enough, I'm going to find some ones that are not as good. Like this one is probably on an edge somewhere, so it got cut. But you see that generally our method worked. Here and there we have some cells that are not perfect, which is what you'd expect. I probably looked at this one already. Come on, give me something bad. This is probably not perfect. This is probably on an edge. This is probably touching another cell. Anyway, you get the picture. So this you don't yet have on your notebooks, but you can please add it in. So just to see that you can play around with it, right? You use this little plus, and you can remove it with an X. So, and again, this is kind of not different from anything we did before. It's just showing a small image. Okay. Now you could think of methods that you can use this information. For instance, if you want to track cells, you can use cross-correlation between these little pictures as one of the measures of whether these two cells are the same cell, right? Or two objects are the same object. So you can think of that. Okay. Now another thing we sometimes want to do is to actually have visual representation of our whole image, right? So we extracted these features, and we want to see whether this actually matches what we'd expect this to look like. Like what the features we got look like what our image started off as. So in this case, I'm going to extract in the same way all of the intensities and all the centroids. Converting everything to arrays is useful because arrays, we know how to work with already. They're like nice and fun. And what we're going to do is we're going to plot the original image, and we're going to do a scatter plot of these centroids. So we're going to put a point at every one of the centroids we found, with the intensity being the intensity of the the color being the intensity of the image, right? So let's see what we get out of this. Okay, so we see that in our original image, we had kind of a brighter region here. So this image is kind of here. You see it like kind of lighter. Can you see it, or is it kind of hard to see? You see there is like this one really, really bright cell that's kind of yellow here. And overall, this looks pretty good, right? It matches what we see by eye. We can make it even nicer. And do you want a moment to kind of copy this? You can also, again, just get it from the repository after the class. But it would be nice for you to kind of play around with putting different parameters up there. So I don't think we've used the scatter function before now, but its inputs are the x. Well, in this case, there is some flips. The image show flips x and y. So kind of the y coordinates, the x coordinates, and the intensities. And also by default, the imshow function reverses the y-axis. So it's, instead of it going from 0 to up to positive, it goes from 0 down, right? So we're just reversing the axes to make them match, but we're not doing anything fancy. The reason I use axis equal is because otherwise it has no reason to assume that the y coordinate, the y units and the x units are the same. It will just give me a stretched out version of the same thing. So when you use axis equal, it tells it no, make sure the scale is the same for x and for y. Okay. You can do even kind of nicer plots. So plot both the information about the intensities and the information about the area, and you can encode area as the size of each one of these points, and intensities as the color of each one of these points. So let's see what this would look like. So you see how like smaller cells are indeed smaller. I'm dividing by 20 just because it gives the areas are too big, and if I just put areas, it would just look like kind of monstrous. But you see how these two things match. And again, this is kind of for visual inspection to know that your segmentation worked, that the features you're getting out actually make sense. Usually when you're doing a real pipeline, you're going to do some manual kind of testing, kind of quality control on a few randomly selected images. And then you're going to, once you're convinced that everything is working more or less fine, you're going to do this for the rest of your data set, okay? And we can even draw these points on kind of the same graph and see that things kind of match. So you can see how, maybe you can see how on each one of these points I have a dot, and the dot encodes the intensity. So you see how this one is really bright. This one wasn't well segmented, so all three of these cells were counted as one cell, right? So this is like one of our errors, but for the most part, we have good segmentation, maybe here and there over segmentation, here and there under segmentation. But this is kind of the general idea of how you present this data, right? And so, okay, so I want you to play around a little bit with presentation. That's okay. I know that this would involve a little bit more copying of code than we were doing the last few days, and I apologize for that. But I think it would be useful for you to kind of get a sense of how to work with these things. Now, the next thing we're going to do is to kind of, instead of, right now we have these big lists, and that they might be a bit non-intuitive to work with, we're going to define some functions that will help us convert this to the table that we were after. Now, I would say that in the newest version of SKI image, which is where we took region props from, there's going to be a function that converts this to a matrix automatically. So we wouldn't have to define these functions and everything, but it's not out yet. So this function was added like a few weeks ago, and it's still not in the default repository. So probably in a month, if you update your repository, this should be, or sorry, your packages, it should be there. But for now, we're going to have to do some legwork to have these functions working. So okay, so let's take a few minutes and just kind of explore this how to represent data and look at our results. Okay. So I think this one is the most general right now. So I'll leave this one on, and you can kind of go through copying it and try and see that you understand what you're copying. And like, should I increase the font size? I think there is a way to increase the font size. Never mind. I only made it worse. Okay. All right. See if you can maybe do like scatter the intensities or the mean intensity or the max intensity, see which one is more informative, which one corresponds more to what you kind of see by eye. See if you can think of kind of other things that might be interesting. Yeah, so I said it's something that was, yeah, and so I added it. So it's in the repository. It should be. I mean, I think that feature one is, Well, it won't be. Oh, no, I haven't put it there. So it's not in the repository, so it's there. So just add it there. Yeah. And then just kind of play around with different parameters. Also try changing the color map to focus scatter. So to get these overlays, you just, you know how here there's two definitions of axes. There's like add axis here, and then another add axis. So if you just remove the second one, it would plot the second, the scatter plot on top of the first one. So that's the only thing that happens here. Does that make sense?
If I want to add onto those circles the number of which that circle falls in like the list of the props.
Again?
Like
oh, you want like
if I wanted to say like given that list of props, number 1 is like in the middle, number 2 is off to the side, number 3 is.
So one way to do it is to say, instead of labeling them by intensities, so you can just call the label.
Okay.
Right. So let's say I'm just going to change it like this, and then this would, now they're numbered from like 1 to however many. Okay. Now, aside from if you just want to have the number, which I guess is more what you were asking, you can just add as text the label next to each one.
Right.
So there is a scatter itself doesn't have like a built-in scatter of numbers, but you can like probably plot.text is like. Again, this is.
I think
yeah.
Stack Overflow is something about annotate. I don't know like what.
So annotate. So I think text and annotate work more or less the same. Only one of them works in figure world, meaning all the coordinates are relating to the figure, and one works in axis world. So everything is relating to the units on the figure, and so.
So that was probably having to annotate.
So annotate probably is the one that's.
One's like an XY argument.
Yeah. So you do.
Oh.
Right. So the XY argument are this and this. Right. And so let's say annotate. So one and 2, and call this. What's the expected input for annotate?
The text that you want to annotate it with is the first argument.
First, and then X and Y?
Yeah, I think X and Y might be a single argument.
Oh.
So it's
That's convenient. Also, what did I do? I also changed the wrong thing. Okay, and let's say here I am. So let's look at number 20.
Check overflow, so you can iterate over all the i's, then label them.
Yeah, but it does seem like it puts all the here I am's in the same place. So let's look at 100. Oh no, it puts in another place, but I'm not sure it's the right place. Let's look at text. The text goes XYS. This seems like it's doing better. Yeah. So I think text is the one you want, and just instead of here I am, you call the relevant label. So yeah, I think that's it. And then you just run it for you. I don't know if text can get list. It's possible that you can, like, get a list of X, Y's, and S's.
Yeah.
So check. Okay, so we are gonna kind of wrap up this part. And so our hopes and dreams starting this workshop was to get to matrix, or a table of features and parameters about objects. So like I said, this hopefully should not be necessary very soon, but for now, we're gonna kind of build our own converter from this list of objects with properties to a table. So the table, and for the most part, when people use Python, is something that called a data frame, and pandas is the relevant package for creating and using these data frames. It's a very convenient package, and we're not going to go into too many details about it, but we're going to kind of briefly mention it and use it, and we'll see what it can do. Now, don't worry too much about all these conversions. You can do what I did, which is look for someone who already did it, list to pandas summary, and just copy it, which is how programming is usually done. And so we have this function. It converts the output of region props to a data frame. Okay, and you can save that function somewhere on your computer, or wait a month, and this should be. So I think there is, in the next version of the SKA image, there is a function called region props to data frame. So it specifically does this. And then very simply, the way we get the, probably shouldn't work here. What is my, oh, yeah, said we did all of this. Something looked odd. Okay, so we define this function. Now when we call this function, it gives us a warning, but we don't care about warnings. It returns exactly this matrix that we were after, right? So we have a list of indices. This is just the label index. And for every index, we have all these features. So areas, bounding boxes, everything all the way to the end, right? We can for instance, look at areas, area, and it will give us a list of all the areas, right? With, so it's a tuple. It will give us, or I guess, dictionary, whatever. It will give us for every label what is the area. We can look at intensity. What is it called? It's called something. Mean intensity. And it could give us this list, which is very convenient. And now we don't need to worry about for loops and anything like that. It's very easy to call everything. Now, finally, very often we have more than one channel that we image, right? And we want to include information about that other channel, right? Now, typically, the mask itself would be the same. So we want to use the exact same mask, just with a different intensity image in, right? So we want to say within this region that I know is cell number 1. So channel number 1 is the first thing that we already have. So it has a certain intensity, certain distribution, whatever. Channel number 2 is going to be a different intensity and distribution, or whatever. And I want to have both of them for the same mask, right, for the same cell. And so I'm going to do the same exact same thing. I'm going to load the image of the second channel. So this is just loading. The first one was 1, and this is 2. This is a different image. I'm going to use the same mask. So label local markers, just with a different image. And this is going to give me So this is the first channel that we looked at, and this is the second channel that we're looking at. You see it's very different. Now, as far as properties go, all of the properties here are the same, aside from the ones that relate to like intensity, that relate to the actual image, right? So it's going to have the same area for the regions it finds, right? Because this is something that's only a function of the mask. The only things that are a function of the intensity image are things that relate to intensity and stuff like that, and the image itself if we want to add it. And so we can just extract only these specific features. So the mean intensity of the second channel, the max, and the min. Right? So these are three things that we care about. I could also add the intensity image, right? So this is also something that's different. So I can do a histogram, and you see it's very different from the first channel. The first channel is very uniform. All cells have nuclei. The second channel is not so uniform because I'm not actually sure what I was imaging there, but it was some of them were very bright and many of them were very dark. Okay. And now to add these features to this data frame that we just created is very simple. We just add another line. So to add another line, we just add another parameter and this. And so now when we look at our data frame, we're going to see that it now has these 2 extra or 3 extra lines, one for mean intensity, max intensity, and minimum intensity. So these are the ones that we just added. All right. And so we kind of successfully implemented this transition from an image to a table with different types of information on it, which is kind of where we hoped to get by the end of this workshop. And so this is kind of the end of the programming part of it. And what we're going to do in the last bit was to kind of go over what's been going on in computer vision over the last, it's 5 years, it's nothing, the last 5 years. So things have been very active over the last 5 years, and we're going to go over it and kind of summarize what we've been doing. So let's take a 10-minute break. And then reconvene and go over, kind of summarize, okay?
Can you go back to your one about the adding the text again?
Sure.
It's giving me I don't know if you got it a bit from.
No, it's here. There.
Oh, you edited it.
Hmm?
You edited it.
Yeah. Happens if I do this. Yeah, it wants one input, so you just need to do kind of a for loop to put all of them in place. So this would be props and dot label. And now it puts a little 11 over here. And then you can do, just run over all of them. So So why do you want to do that? Just
So that's essentially how we do it. The imaging process right now is we sort of like we use this program that doesn't work that great, so I'm sort of trying to imitate it, but and it will label.
Which program?
EZX and EZX analyzer.
Mhm.
And so, yeah, so when it outputs the image, it will label each cell with a particular number that it corresponds to.
So it like labels, yeah. So
Right,
it does the same thing.
Right.
Okay, that should work.
Yeah, sorry, for some reason I got the error from here. I don't know. I could not solve it from the scratch actually. So
Oh. So here you're giving it markers, but you then define markers after.
it should be before.
What is what's happening?
It's not
Oh. How is this computer, by the way?
It's very fast.
Do you like it?
Yeah.
Yeah.
It's the recent version of the
So my computer, a few days ago, just died. So I have to. No, I went and reinstalled an older operating system. Now everything works, but I know I'm on borrowed time. Sorry. It'll be hard for me to please do not. No. I'm saying I was actually looking at this specific computer. So what changed? So did you run everything prior? I guess so.
Yeah, I had it yesterday, but today.
Yeah. So this is like shortcut. So usually like so what you call or yeah. So you say for R, which is like R at each of those R's you get the mean. Yeah, it's really cool, but yeah, it's a little bit backwards for the end.
I guess what I'm confused about is this R with the MCs, right? In channel, so not like the whole list of stuff. So it goes through the length of it?
Not through the length, it goes through
All the objects in the list. So, yeah, so you can do a for loop over a list, and it just will go over all these objects in the list.
yeah, so the like observation of the list is the attributes.
Down memory. And they probably just don't have something like a parameter to define before, and then it turns over.
Well, not necessarily, because essentially, like, I mean, the numbering is a little bit arbitrary, right? Just here's the, data thing, right? So it's essentially, I just want, these numbers, because the programmatic crazy is sort of numbers like this. But then I want to be able to go back to the and say, okay,
They just don't have some. Yeah.
Okay, so when I was trying to run this code, or just like this thing part where we get to the session, notice that if you want to type in, for example, just prompts or prompts 0 or something.
So if it's the last thing in the so that it only prints it if it's the last thing. Otherwise, you say print.
Okay, then if I say print, then it should work. Okay, that's
So if it's the last output, prints it. It's open.
So okay.
But otherwise,
okay, and then another question is okay, so prompts is very long or something. I don't know. Okay, I use MATLAB, so that's why this is so weird to me. I only know MATLAB. So MATLAB's very nice because you just click on the variables, you can see it. It just makes so much sense.
MATLAB also has a region prompts.
Yeah, it has something like that.
MATLAB region prompts what you get out. So you have to define what the parameters you want to get out. You get out a data structure. And then that data structure is going to have different properties.
But I guess my question is is there a nice way to show this? This is very ugly.
Well, so the nice way is down with the data frame. The reason this is very ugly is because this is basically going to be props is a list. This is an object. This number is an object. Each one of these objects has a bunch of different properties.
Okay.
So this is
yeah.
So MATLAB is its object-oriented abilities are kind of not really. They're there, but you can see that they've been put there after the fact.
Yeah.
So for instance, the idea of the data structure is really what it is, kind of a data container. And it isn't an object for you can call things like data, whatever is output. But it's not natural.
Yeah.
Here, everything was built to be from start. I would say that I don't think particularly that Python is better than MATLAB. I think.
Isn't it faster?
It used to be faster because MATLAB used to be very slow in for loops and stuff like that.
Yeah.
But this is historical. So people say it's faster, but it's not faster. MATLAB implemented something called just-in-time processing a few years ago. And just-in-time processing means when you run a for loop, the first iteration basically converts your code to C. And then it runs all the for loop in C. And so a for loop in MATLAB is actually faster than a for loop in Python.
Really? I thought MATLAB was very slow.
So MATLAB is not any slower. The only real downside of MATLAB is that it's expensive.
Yeah.
But in terms of with MATLAB, because you're paying for it and because everything is maintained in one company, you're never going to have problems of packages not talking, not acting right with each other. So honestly, I think it's better, but it's much more expensive.
When did they make that change?
Why? Like 8 years ago or something like that. You can look it up. It's called like just-in-time JIT.
Wait, what just-in-time? Just-in-time?
Look up MATLAB just-in-time on JIT, but I think people still have this historical idea of like, oh, for loops are so slow in MATLAB.
Yeah.
Like, yes, 25 years ago they were slow. Also,
Yeah,
if you're doing
says that all the time.
if you're doing for loops in MATLAB, you're not doing it right. That's also a little bit different.
Yeah.
So much of our code base in the lab is actually MATLAB.
Yeah.
And we found in many cases that doing for loops, if you implement them right, and if you kind of think that like, this will become C at some point, are faster than even vectorization. You know, like with MATLAB, they tell you like vectorize everything, and sometimes it's not the case. It'd be faster to just do it for loop.
In all my classes, I was always taught that the for loops are still. I mean, it was around 7-8 years ago, and I learned it. Somebody like before.
So it's realigned.
Yeah. This is just in terms. I don't know. It's explained.
So it like compiles everything during the first iteration, and then it's really, really fast.
Yeah. That's good to know. Thank you.
Sure. Don't trust the cool kids on Twitter who tell you that MATLAB is bad.
Yeah.
Well, it's free in UCLA, but it's not free really, right? It's like someone is paying in the sense that and one day you're going to leave UCLA, and if all you know is MATLAB, then some employer is going to be upset that he has to buy a license just for you.
Any difference between the MATLAB student and MATLAB professional, or like the MATLAB regular one?
I think packages are a bit different. The core is the same. I was going to give you like you can only do multiplication, you can't do addition. I think it should be fine. Okay. All right. So we are more or less done with everything we set out to do at the beginning. So I told you at the beginning this is an introduction, and I hope that during these 3 days you kind of acquired some basic understanding of what computer vision is and kind of the fundamental ideas of how things are done. I also really hope that I managed to convey the importance of being systematic in how you analyze your data, rather than like making circles and arrows. Now, on our way to getting these, I also hope that you got a little bit more confidence in programming. So I think often people think of programming as kind of this like very daunting task that you open a blank piece of paper and now you need to program. And this is not usually how it's done. Usually you start off with some core that you get from either from somewhere else, like the internet, or from some examples, and you kind of build from that. And this process of programming, which is actually the real process of programming, I hope is a bit less intimidating. And that's also true about like how the heavy use of the search engines during programming is how things are done. It's not like a cop-out, it's just what it is. And so always go back to the manuals and go back to like the APIs for the different packages and see what it's capable of and what is already implemented that I don't need to sit and waste time implementing myself. We talked about how this is our goal, right? We want to take imaging data and convert it into a meaningful list or table of features and details about these features that we can then go and analyze, and we can then go and learn something interesting about these monkeys. So just the image, this step alone isn't yet science, right? The science part happens after this. And the more interesting and more exciting part usually happens after this, right? So this is also something to keep in mind. Now, I pointed to some more resources. So like I said, this is introductory. I hope you got a foundation that would make it much easier for you to step into any one of these courses. I think I had more resources in the intro. You'd be able to step into these things pretty comfortably and start doing more complex things. And also, you should be in a place where you can read kind of basic image analysis papers and understand what they're doing and have a general sense of how things are done. Now, let's kind of talk about everything we've been doing so far, like in this class, in terms of approach, and what exactly does that mean in terms of how computer vision is defined. So we started off kind of with very low level computer vision, which is just the image signal, right? We have information in the shape of photons coming from the environment, and then you can do kind of low level operations like denoising, thresholding, stuff like that. Then from that, we move on to kind of more intermediate level computer vision, where we kind of condition our image on certain signals. We define what's interesting and what's not interesting, and then everything that's like kind of masking, right? Masking is like a more advanced way of looking at your data because you have some prior information on what's interesting and what's not. And that's also true for filtering, right? So I'm looking at specific features and what they're telling me. And then from that, we went to like these image-derived parameters. So that's kind of more high level, right? So now we actually have an idea of what is in our image and what are different properties of these objects in our image. So this is kind of more feature extraction, feature engineering, kind of selecting how we want to look at our world and what features we want to highlight. Now, the one thing you probably noticed about all of these things is that all the parameters that we defined were more or less defined by hand, right? So we decided how big a cell should be, and we often got this question of like, how do we pick the sigma? How do we pick the size of a window? And a lot of this was, trial and error. You pick a number, you see if it works, and so on. So there are many like kind of user-defined and many heuristic ideas on I'm going to define the wheelness of this object by kind of comparing it to my representation of a wheel, right? So I have a filter that's the shape of a wheel, and I'm going to say, is this a wheel or is that a wheel? And this, for the large part, was the state of affairs in computer vision circa 2010, 2011, right? So this was kind of how things were done. If you wanted to do computer vision, there were these things called filter banks, and they were online, and you would go and find all the filters that might be relevant to your data, and you'd run different filters over all of the images you have, and you'd see for different scales and different rotations and stuff like that, and you'd find different objects, and you'd be very happy that the wheelness of my car is 7. Now, what happened in 2012 was kind of a breakthrough in computer vision. So AlexNet, named after this guy, Alex Krzyzewski, came on scene, and this was kind of the onset of deep learning. So I think Geoffrey Hinton just won some big awards, so that's good. So the idea is very different from what we were doing so far, right? And what the world was, he won ImageNet in 2012, and I think he then won it for 6 straight years using this. So ImageNet is this like open competition of image classification and segmentation, right? And for a very long time, things that are filter bank derived were winning, and then he came and just blew out the competition for like 6 straight years. And then everything that won after that was based on the same approaches. And the idea is these like deep convolutional neural networks. Deep convolutional neural networks are actually not a new idea. They've kind of been around as an idea, as a concept since probably at least the 80s and probably even earlier than that. Since the 40s. Some theory was around since the 40s of like perceptrons, but kind of a deeper idea of how to implement this has been around since the 40s. But they were always considered kind of like a neat idea, but not really feasible. So I can give you an anecdote. I recently did I read this book called Learning from Data. And it's a book that was It's based on a course that a professor gave in 2011. And in that course, he talks about kind of the idea of like kind of the theory behind data science. And then specifically, he talks about different topics. And he talks about artificial neural networks. And he describes artificial neural networks as this kind of niche field that no one cares about, that only a few banking services use to define who's like creditworthy and who's not. And here and there, you'd see a paper or two, but you know, don't spend too much time like worrying about artificial neural networks. This was at the end of 2011. A few months later, AlexNet came on the scene. Now, if you have any idea of like what's been going on now, I think every person I went to college with now works in deep neural networks. So it kind of took over the entire field of computer science basically overnight. So what exactly are artificial neural networks? It's more or less inspired by biology. It's the idea that a system that is very multi-connected and has many layers can learn features about its environment and can translate these features into some desired outputs. These systems need to be trained by providing them a large set of data that's annotated. So this is usually called the training set. And so we have an idea of what they should do, and we give them just examples of like, this is what you need to start with, and this is how you need to end, and good luck. And there are a set of algorithms that are trained to, that are built to kind of train all of these networks. And we're going to very briefly say what these networks are actually doing. And ideally, after training, they can interpret new data that they haven't seen before, right? So this is the hope. Now, this is really, really a new field. So the theory behind why many of these things work is kind of up in the air. But the fact is that in many cases, they do work. So a specific type of these artificial neural networks is what we call convolutional neural networks. And now you remember when we talked about filters, we said that what the mathematical operation that filters are doing is formally a convolution, right? Right. So that's what the idea behind convolutional neural networks is that what we're basically learning between these different layers are the filters. Right? So the filters that we beforehand defined by hand and said, this is good for finding if something is round, and this is good for finding if something is, I don't know, big. Now we're going to have the computer learn the shape of these filters on its own. And the problem is that many times the filters that it learns are not really interpretable for us. We don't understand what they mean, but they have some information in there. These networks are built kind of in a layered way, where in every layer you can learn different scale of features. So on one, you can kind of learn like big scale features, and then like you go into more fine details. The convolutions give you, you know, they make the size of them smaller, and then there are also, Wahid is not here, but he was talking about kind of pooling of data. And so the idea is that I keep focusing on smaller and smaller details as they go down, and eventually I get into kind of like very simple representations of my data that can then, that are learnable. And so what we're talking about is kind of a very big conceptual change in how programming is done. So traditionally, programming is done by, we have an input, we design a program around this input. The logic is predefined by us, right? We give the logic, we say, if you have this input, you should do this, and if you have that input, you should do that, and we get some output at the end. The idea of machine learning kind of switches that around. So for machine learning, what we're giving the computer is the input and the output. And we're asking the computer to learn the logic from the examples we're giving it, right? And so the big algorithm that makes this possible is something called backprop, so backpropagation. The idea that we can take some error in how well we can recreate data and propagate it back to parameters that are further up the chain. And so by that, learn these filters and learn what are the filters that make any sense of this information. So just to get a sense, so as of October 2019, this paper that is 7 years old has about 50,000 citations. It's not technically the first implementation. Their big breakthrough was that they were able to run everything on GPUs, and GPUs are really good at doing these convolutions. So before that, that was the thing that was kind of the bottleneck that we just couldn't run things fast enough. So you can train it, okay, but it would take you 100,000 years to train your neural network, and then what are you going to do with it? Running it on a GPU made everything much faster, and they brought it down to like reasonable times. You can also see the explosion of GPU use around that time, and it also strangely coincides with the appearance of Bitcoin, which is also GPU based. So yes, actually the crash of Bitcoin made eBay full of cheap, good GPUs. So you can go and buy good GPUs whenever Bitcoin crashes. So that's a good thing to know. Okay, so the next kind of big step was going from just image classification to actually giving a description of your image, right? So eventually what we care about is understanding on the level of human language. We don't just want to have a set of numbers that define an image. And I'll tell you, lambda 7 equals 3 and lambda 3 equals 1, and therefore this is, an image of a goat. We want to have something a bit more human interpretable. And so between Google and some researchers at Stanford, what they did is to actually train 2 neural networks, one to deal with the part that is vision. So, taking an image and bringing it to a set of features that is interpretable to a computer. And then another neural network that takes these set of features and translates it, basically generates a description, right? So now you can take a picture of this room, load it to Google, basically, and you'll get a description, classroom with computers and students sitting, right? So this is kind of a big step. And so after kind of that became a solved problem, image classification became not only the idea of like, it became more descriptive. So we went from just saying we have these objects to actually saying what's going on in the image. So now this is kind of the capabilities of kind of modern networks. So you have this picture, and you immediately get out of it that these are 2 young girls playing with Lego toys, right? So so that's pretty cool. Okay, and then how does this relate to us, right? So biology, and when did this come in on the scene for us? So the first paper that used this for any kind of biological application came in 2015. That was UNet. It was kind of built, so it's called the UNet because it's shaped like a U. And the idea was very similar to what was going on before. So it's like a layers of convolution. It brings it down to a simple low-dimensional description of the data, but then it builds it back up to an image that's segmented, right? Because we don't usually specifically care about having a description 7 cells sitting on the glass plate. We want kind of segmentation of our image or something like that. And this was specifically built for biomedical image segmentation. And ever since then, there have been many implementations with like different variations, different pre-processing. Now, maybe I should also say, this is not magic, right? So the fact that these things exist and they work, it's not like a completely solved problem. First of all, because there is the issue of I'll get to the issues in a bit. Okay? So this is kind of what's happening in 2015, and then the hope is that in the future it would become even simpler. So you wouldn't need to know any of the underlying computer science to be able to use these things. And you're already seeing kind of the first examples of that. So there are these two projects that I know of, and probably there are many more. So one is DeepSaw, and it's by the Van Valen lab at Caltech, our neighbors right here. And Nucleizer, which is a horrible name. AI is like artificial intelligence, right? So that's bad pun. And these things are right now like online, and you can just go there and grab an image and drag it in, and it would return a segmented image, right? For the most part. Now, so hopefully this is something. This field is moving so fast that probably these slides that I made a month ago are already irrelevant. But there are still open questions in this field, and one big open question is kind of like interpretability of these hidden layers. So we have, the computer is learning, the joke is like, the computer is learning, we're not learning, right? So we don't understand what it's doing, and so it's probably, it would be a while before we have a good sense of what's actually going on. The other problem, which is kind of a big difference from us, is that humans are actually very good at learning from a small set of examples. So if I show you one picture of, if I show my 3-year-old one picture of cells, and then ask him to find cells in 50 other pictures, he would be very, very good at this. He would not need much more than that. Computers aren't very good at this. So computers need a lot of reinforcement, a lot of examples before they're actually any good at recognizing computer or images. So for now, at least, it's not like exactly how much and in what way these things should be used in biology is still debatable. And specifically, it's becoming more clear that using this for kind of routine tasks, so things like image segmentation, is fine, right? So in places where we're just taking something that we can do on our own, like we're pretty good at image segmentation. We can understand if something is working or not. And basically it's an automating tool, right? So this is something that can do it much faster, much more efficiently. So this is probably a good use of machine learning at this point for our needs and for science in general. But using it for generating new hypotheses or kind of learning new things about the world is probably not yet, we're probably not yet there, mostly because we don't understand what it's learning, what it's actually doing. And so it would be very prone to giving us an answer that, okay, we don't know what it means, we don't know what it does. And so the other thing is that it's trained on annotated data. So it's trained on the things that we tell it to train on. And so almost by definition, it can't learn things that are far out of what we expect, right? So there is a lot of resources on this online, a lot. There is a machine learning collaboratory workshop that's sometimes given. I don't know if it's given next semester, but we should pick it up. There is a very, very popular Coursera on machine learning that you might be interested in taking. And again, this is a very partial list. If you just Google machine learning classes or deep learning classes, you would find a list of infinite length. It's infinite because while you're searching, more of them are getting added. So, and I think that is more or less it. So, any questions, concerns, ideas about the course or about anything else? Anything you want to share with all of us?
So with the machine learning implementation, do you think MATLAB is still as good as this Python, or do you think what?
So that's another problem. Yeah. So some of you might have heard, or maybe not, that we're talking about like MATLAB versus Python. So one of the issues with proprietary software is that it's slow, right? So between when something comes on the scene and when it's implemented in a proprietary software, it takes relatively a long time, whereas open source, it's immediate, right? Like the day after someone writes a paper or an algorithm or conference talk about whatever it is they're developing, they put it up on GitHub and they make a little Python shell around it. And so you do lose a lot of this, like you're less nimble when you're a big company and you need to make sure everything works together and everything. MATLAB are coming up with machine learning stuff, like they're trying to catch up, but you're always going to be behind. There is no way around it. The question is, do you always need to be cutting edge in everything you do? Right? And usually the answer is no. You don't really need like whatever was published yesterday for your research in a different field. And so that's generally my answer.
Are there any other programming languages that are common in machine learning, or is it mostly Python?
So I'm not sure. I think many people use Python. I mean, let's separate machine learning from deep learning, whatever. Machine learning you can do in any everywhere, and you can also do at this point deep learning in R and in Python and MATLAB. Whatever. The algorithm itself is not language dependent. It's just what language is the community mostly working in. As far as I know, most of the community is working in like TensorFlow and its implementations in Python. But I might be missing big chunks of it, right? So like TensorFlow, PyTorch, so PyTorch, right? So that's the. All right, so as Eloy mentioned, there's going to be some survey that he will send. So please help us get better in whatever way you think we're lacking, and also just your feedback would be very valuable. And thank you all for your time, and I hope this was useful for you. And see you around.
Thanks so much.